Hi folks, so I'm going to take a look at the solution to number 10 on page 460. So here they're asking us to determine the equation of the plane that contains this point and the given line. All right, now they don't specify which version of the equation they want. This is in the vector equation section, but I'll just find the Cartesian equation too while I'm at it. All right, so let's take a look at what we have. So if we let this represent my plane, so this plane contains the point, okay, negative 1, 2, 1, and the line given by this equation here. All right, so if I want to find the vector equation of this plane, the first thing I want to do is to determine a point and two direction vectors. So point, well, here they give us a point outright, and in fact there's another point, 2, 1, 3, that also works, because if that point is on the line and the line is on the plane, it means that point is also on the plane. So we have a choice of points, doesn't matter which one we use, and we need two direction vectors. This is where I realize that since this line is already on the plane, then its direction vector can also be used as a direction vector for the plane. All right. Thing is, we have to come up with a second direction vector. So the way I'm going to do that is I'm going to join the point on the line with this point that presumably is not on the line, okay? And use this as my second direction vector. So notice here I say presumably, because if I determine this vector and it turns out to be parallel to the direction vector of the line, well, that must mean that this point is also on the line because it's creating some vector parallel to that direction vector. So hopefully it won't be. By the way, if it were on the line, it means there isn't enough information to define a particular plane. All right, so as a point, I guess I'll take 2 and 3 since no negatives there. Okay, it doesn't really matter which one you use. As my first direction vector, I'm just going to take the direction vector of the line, which is 4, 1, 5. And then for my second direction vector, I'm just going to join these 2 points with a vector. Okay, so negative 1 minus 2 is negative 3. Here we've got 2 minus 1 is 1, and here 1 minus 3 is negative 2. Okay, and I could have even gone in the other direction. That would have been perfectly fine. But the important thing is that when I look at these two vectors, I see that they're not parallel. So now we have enough information to write the vector equation of this plane. So vector to the point 2, 1, 3 plus some parameter times my first direction vector, 4, 1, 5, plus another parameter times my second direction vector, negative 3, 1, negative 2. And here S and T can take on any real values. Okay, of course, I could also split this up into the three components and write this in parametric form. So I might as well do that. X is equal to 2 plus 4S minus 3t. Okay, now we're going to look at the y components. So 1 plus s, okay, and then plus t. And then lastly, z is just going to be 3 plus 5s. And then here, minus 2t. And again, s and t in R. Okay, so if we want to find the Cartesian equation of this plane, well, we're going to need a normal vector to this plane. So here, let's draw some normal vector. And the normal vector, if it's going to be perpendicular to this plane, of course, it must also be perpendicular to the two direction vectors. And so this is how we get this normal vector, by taking the cross product of my two direction vectors. Because what does that give me? A vector that's perpendicular to both. So something that's perpendicular to these two vectors will also be perpendicular to the plane. All right, so let's take my vectors, negative 1, I'm looking for the vectors, so it's going to be 4, 1, 5, and then we have negative 3, 1, negative 2, and I'll bring these over, and let's take the cross product. Okay, so my x component is going to be negative 2 minus 5, negative 7, all right, and here I've got negative 15 minus negative 8. So negative 15 plus 8 looks like it's going to be another negative 7. And then here we've got 4 minus negative 3. So 4 plus 3 is, well, 7. There we go. So nice normal vector. Now, since I know that this represents the coefficient of x in my Cartesian equation, and I would prefer having a positive number there, what I'm going to use is my normal vector, because n is going to be just, in fact, I can do even better than that. Instead of taking 7, 7, negative 7, I can simplify this even more. Because remember, any normal vector is valid to find the equation of the plane. I might as well use the simplest one. So I'm going to multiply this by negative 1 over 7 to end up with 1, 1, negative 1. Okay, this means I'm going to have less simplifying to do later on. Okay, so now that I have a normal vector, I can use either of my points to determine the Cartesian equation of this point. Okay, so let's say I use 2, 1, 3. In fact, I'll use the other point as a check to make sure I get the exact same equation. All right, so remember that our equation looks like ax plus by plus cz plus d equals 0. Okay, so let's start with my normal vector is 1 times, let's start with negative 1 to 1. So 1 times negative 1 plus 1 times 2 minus 1 times 1 plus d is equal to 0. And let's see what we get. Negative 1 plus 2 is 1, minus 1 is 0. So d is equal to 0. And just for the fun of it, let's check with the other point to make sure that we get the exact same answer. Okay, that'll tell us that we haven't made an error here. Okay, so I won't bother with this. So the normal vector is still 1 times, except now I'm going to work with 2, 1, 3. 1 times 2 plus 1 times 1 minus 1 times 3 plus d equals 0. And so what do we have? We have 2 plus 1 is 3, minus 3 is 0, d is 0. So that's just like a check that we got the right answer there. So in the end, what's our equation? So it's going to be ax, so 1 times x plus 1 times y minus 1 times z, okay, is equal to 0. All right, and there we have it. We have both the vector equation and the Cartesian vector equation, parametric equation, and then we were able to find the Cartesian equation. Okay, so just to recap, because this first part would be the same regardless of what equation I'm looking for. Okay, I know I need a point on the plane. Okay, now if I'm looking for vector equation, I need two direction vectors to be able to write out the equation. Okay, but even if I'm looking for the Cartesian form, I still am going to use these two direction vectors so I can cross them to get my normal vector. All right, that's it for this one.